Hey everybody, and welcome to video number 1 of our Unit 2 on bonding, where we try and uncover the story of bonding between atoms and show how this is really just the story of these atoms and their eternal search for happiness. Throughout the course of the video, we're going to be focusing on two particular atoms, lithium and fluorine. And we're going to look at lithium and fluorine because they're both extremely unhappy. As it turns out, they're unhappy because of their electrons, but we're going to get into all of that later. Before we start, everyone needs to be aware that this term unhappy is really not an appropriate way to describe atoms. They're particles. They don't have feelings, happy or sad. So when we say that an atom is unhappy, what we're really saying is that it's chemically unstable in the form that it's shown. It doesn't want to exist in that particular form. Another way to say unhappy would be to say that these atoms are in a higher energy state. So let's take a look at these unhappy atoms a little more closely by covering some terms. Most of what I'm going to say should be review for everybody watching this video, so I'm going to go pretty fast. Remember, you can stop, pause, and go back at any point if you're confused. Number 1, we have something called valence electrons. The valence electrons are the outermost s and p orbital electrons. Why we care about those is because those are the electrons that interact, for the most part, with other atoms. Let's bring up our lithium and our fluorine and see if we can find their valence electrons. First of all, if you look at the model of lithium, its outermost electron is very clear, the outermost one there, flashing red. You should also be able to find the valence electron from the electron configuration shown here. The way to do it is to go to the highest energy level, which is of course the second, and just count how many electrons are in the s and p orbitals there. Of course, there's only a 2s, and there's one electron there, so that is lithium's 1 valence. If you do the same for fluorine, its outermost are these 7, flashing in red. On the configuration, you go to the highest energy level, the second, count the s and p electrons, 2 plus 5, give you fluorine's 7 valence electrons. Now, this is a really important skill, so I need everyone to practice this for a second before we go further. You can pause the video, try this on your own, and then hit play to check your answers. Okay, so here's the official answers. If you do sodium's configuration, it goes up to 3s1. The highest energy level there, of course, is 3, which only has an s1, so that's sodium's 1 valence. Chlorine goes up to 3p5. Its highest energy level is also 3, but now there's s's and p's, so 2 plus 5 are 7 valence for chlorine. Strontium is much bigger. It goes all the way up to the 5th energy level, and there's only an s orbital there with 2 electrons, so this is strontium's 2 valence. Lastly, selenium goes up to 4p4, so it goes to the 4th energy level where there's both s's and p's. 2 plus 4 are selenium's 6 valence electrons. Alright, so hopefully you did okay. Let's move on to the next term here. After valence electrons, we have to talk about something called Electron Dot Diagrams. These are a really simple way of representing an atom, which shows only the valence electrons, since those are the ones we care about most of the time anyways. Here's lithium again. We already know lithium has 1 valence. Here's how you do its electron dot diagram. Start off with just the element symbol, Li. Then you put 1 dot around the symbol to represent the 1 valence. My dot is on the right. You could put your dot on the left, the bottom, or the top. It doesn't matter. We'll do the same for fluorine. We already know that fluorine has 7 valence. Here's how you do its electron dot diagram. Start with the symbol, capital F. Put 1 dot. You got to put 6 more to get up to 7, but pay attention to, because the order, the place you put them matters here. Each electron has to go by itself on one side of the symbol first. So if I put one on the right, the next one could go on the bottom. The next one on the left, the next one on the top. Only when you've put 1 per side, now you start to go double up. So the 5th can double, the 6th can double, and the 7th can double. Make sure you follow that same order pattern when you try these on your own. Now would be a great time to do so, so pause the video, see if you can write the electron dot diagrams for the following 4 elements. Alright, here's the official answer. Sodium has 1 valence, so it should have just 1 dot on the right, left, top, or bottom. Chlorine has 7 valence, so you should only have 1 unpaired electron. Strontium has 2. They should both be on their own side, unpaired. Selenium has 6, so it should look like 2 paired electrons and 2 unpaired electrons. Okay, we have one final rule to go over here before we're done for today, and that is something called the Octet Rule. The Octet Rule tells us why atoms bond to each other in the first place, and the rule is that most atoms bond in order to have a noble gas electron configuration. What this really means is full s and p orbitals for these atoms, which usually correlates to 8 electrons in the outermost shell. Let's take a look at how this works with lithium. We can easily see that lithium is unhappy there, but now we sort of know why. Lithium is unhappy because it does not have a noble gas configuration. So what lithium is going to want to do is change its valence electrons. It actually wants to lose that outermost one, so it loses the entire 2s energy level and drops back to just the 1s2. Why is 1s2 good? Why does that make lithium happy? It makes lithium happy because now it has the same electron configuration as helium, which is, of course, a noble gas. Fluorine does a similar thing, but a little bit differently. Fluorine is not happy with its electrons, but if it could gain one more, then it would go to 2p6. That would make it really happy. And what's so great about 2p6? That's the same electron configuration as neon. And guess what? Neon is, of course, a noble gas. So that concludes our video. These 3 terms are the basic ideas you need to understand how and why atoms bond to each other, along with one more really important one. This full shell of paired electrons, like we described in the Octet Rule, like noble gases have, is what we're going to call a low energy state that all these atoms are trying to attain as they bond to other atoms. Thank you very much for watching, and please enjoy the short recap on the following slide.